explanation of the free body diagrams that I went over with my classes on October 18th, Thursday, but one of my classes was unable to attend due to the college fair. So I want you to be able to go over this and do this at home so that you can have this written down and won't get you a day behind. So this is the free body diagrams, Physics 1. A free body diagram shows all of the forces acting on an object using vectors originating from the center of the object's mass. Each force should be properly labeled. The sum of all these vectors is the net force, summarized as a sigma F. So the first example is a box being pushed across a frictionless surface. The force pulling the box down is its weight. So you can draw a box or you can draw a dot. Here they did both. And so from the center of the object downward is the F sub g for weight or gravity. The reaction force of the surface pushing up is the normal force, F sub n, so it's opposite of the gravity. And then the force pushing the box across the surface is F sub a, and it's usually in the rightward direction unless specified directly to the left. And since the weight and normal force are equal and opposite, the net force is equal to the applied force. So because it said it was frictionless, we're not drawing the friction occurring in this free body diagram. And so the overall net force is applied. So here they drew an arrow to the right and wrote the sigma F. I prefer to write sigma F is equal to the applied force. Okay. Also, I need to mention that when you have forces in a right direction, we normally consider that a positive direction. So anything moving to the right is considered positive. And this is just like your coordinate system in math when you're graphing. Anything up is also considered positive. Down is negative direction, and to the left is negative also. Okay? So keep the coordinate system in mind. They'll come up in a few of our examples. Also, I want to look at the definitions that are on the back page. Forces you should know. Gravity, we use F sub g. The force of attraction between an object and the planet is also known as its weight. And it's always written toward the center of the earth, F sub g. Normal force is the reaction force of a surface on anything pushing on it. So anything that's sitting on a table or in a chair, okay, the normal force is what's holding it up as opposed to gravity. Tension, or F sub capital T, the force that holds a string or rope together. So if you have an object hanging by a rope or a string, that's what we call tension. Pulley, elevators, and those sorts of things are being pulled by cables. Friction, F sub little f, force caused by surfaces rubbing together, acts to oppose friction. So if an object is moving in this direction again along a surface, then friction is always moving in the opposite direction of that applied force. Drag, F sub capital D, force of a fluid exerted on anything moving through it. That's the air resistance. So if we have like a parachute, Okay, and the little person down here is parachuting. It's attached to his head. And so the drag that's being caught up in the air or anything like that is the drag. Thrust, and I prefer to have F sub TH here since we already had F sub T. It's the force from engines, rockets, etc. that propel an object forward. So again, I'm not an artist, but if you were to have the force, the thrust is coming from the engines. That's your rocket. And then F sub L is lift. It's the upward force that causes airplanes and other flying objects to fly. So your airplane has a lift, F sub L, that holds it up above the ground. Alright, so those are the ones we'll be using, and I promise I won't draw anymore. I'll just stick to my stick figures. So it says, draw a free body diagram for each object. Be sure to include the net force. If the net force is 0, the forces are balanced. Indicate sigma F equals 0. So a box being pulled with a string at a constant velocity against friction. So I'm just going to draw a dot representing our object, and it's the center of gravity of that particular object. There's always the object's weight is pulling it down toward the force of gravity, and it's on a surface, so normal force is holding it up. It doesn't specify which direction the string is pulling the box, so we just assume that it's in the positive direction, which would be to the right, and then the frictional force is in the opposite direction of the applied force. So I'm just going to write these words out since these are the first time that I've used them, and I'll just stick to the letters from now on every time I use them, but when I introduce a new one I'll write it out. But since it said it was going at a constant velocity, that means these two things are balanced out. So our net force is equal to 0. There's no overcoming force. Now our rocket-powered sled accelerating from rest on ice. So it's obviously got an applied force. Again, it didn't say in which direction, but now since it's rocket powered, we call that thrust, so TH. Again, that's a new one, so I'm writing it out. Force of gravity down, normal force holding it on the resting on the ground, and then the ice is rubbing against the ice. There's some friction, but there's not much friction. Obviously on ice it's less, but since it's saying it's accelerating, that would mean that the net force is coming from the thrust of the power. Okay? Then 3, a box sliding to a stop on a rough surface. Alright, so this dot represents the center of the box. F sub G is the weight, F sub N. Now it says it's coming to a stop. So friction is being applied to the box. There is no applied force necessarily. It doesn't say that it just talks about that moment in time when it's sliding to a stop. So there's no applied force in this case. It's already in motion and now it's coming to a stop. And because the friction is overcoming that motion, we say that the net force is equal to the friction, or the frictional force. But we don't have a number, so we just refer to it as friction. Okay? Number 4, an airplane flying straight and level at a constant velocity, the thrust of the engines must overcome the force of drag. Okay? So, center point of our airplane, this gravity is always pulling on it. This time, an airplane up in the sky, what keeps it up in the sky is what we call lift. Okay? Again, it's got thrusters, so the thrust, and now it's going through air, so according to our definitions we had on the back, is drag, the air resistance. Okay, so 2 new ones, the lift force and the drag force. Because it said it's going straight, level, and at a constant speed, all of those forces are in balance, so our net force is equal to 0. Okay, so within these first 4, we demonstrated normal force and gravity, applied force and friction, thrust in the case of an engine or rocket, lift, and drag. Okay? Let's look at number 5. A group of football players pushing a blocking sled against friction. So it didn't say what direction, it didn't tell me accelerating or constant velocity. I think that was something that might have been left out of this problem, so I'm going to add in, let's just say that it's moving at a constant velocity. So center of the blocking sled, normal force, gravity, there's a applied force, and there's a frictional force. And because I indicated that it was, think of it as constant velocity, then our net force is equal to 0. If they had indicated that it was accelerating in this particular problem, it would be the applied force. If it said that they had been slowing down, it would have been frictional force. Okay? A bucket hanging still has gravity pulling on it. Now it says it's hanging from a rope, so this one is our tension force. Okay? But it's not moving side to side, there's no pushing, it's not even moving down or moving up, it's just hanging there, so still our net force is 0. Okay? 7. A hockey puck slides across a frictionless ice at constant speed. And this is one of those cases where it's the fairy tale imaginary scenario. So gravity, normal force. We know that there's hardly anything that's completely frictionless, but since they indicated frictionless, that meant, we weren't to draw anything in the friction, and that there's already been an applied force at some point. It doesn't talk about something still being applied to this hockey puck. It's in a constant speed. It was sent in motion and it's staying in motion. So because it's at a constant speed, the net force in this case is still 0. There's no constant application of applied force. Okay, now the bucket from number 6, after the rope is cut, Okay, now we have the bucket is falling towards the ground. There's not a tension force on it anymore, that's been cut, but as the bucket is falling through the air towards the ground, there is some amount of drag. Now it's not going to be enough to still hold the bucket up in the air. It's not enough even to slow the acceleration toward the earth. So now in this case the force of gravity is the net force. So I'm just going to write the force of gravity is equal to the net force. 9. A man standing in an elevator that is accelerating upward. This is one of those scenarios that you have to pay attention to. What is it asking about? So in this case I have to do a drawing. This is our elevator. The man is standing in the elevator. There is a cable holding up the elevator, and it is accelerating the elevator upward. There is the force of gravity pulling down on both the elevator and the man standing in the elevator. The man is standing in the elevator, and the floor of the elevator is holding him up. So that's a normal force. Because the question is referring to a man standing, the scenario we're looking at here is the man in the elevator, not the elevator itself. So because the man is standing flat on the floor of the elevator, the net force, according to him, is 0. If the question were to ask about the elevator, and because it's accelerating upward, it's obviously in the tension force. So pay attention to which scenario it's referring to. Alright, a falling rock. This is about as good as my drawings get. Okay, and according to this it says no drag. So we have the force of gravity here pulling the rock down, and that's our source of our net force. Okay, a helicopter climbing at a constant velocity. Gravity is always pulling it down, but then the helicopter going into the air, that's a lift force, but it's saying that it's going at a constant velocity, so it's moving at a rate that would equal out the pull of gravity, so our net force is 0. Alright, but then over here it says a helicopter accelerating upwards. So now we still have the force of gravity, but the force of lift is accelerating faster than the pull of gravity, so that is our source of our net force, is the lift force. Okay? Just one more review over that. These things are being pulled down. This one is frictionless. This is referring to just the man in the elevator. Rock falling. Helicopter at constant velocity. Helicopter accelerating. Okay? And then in this page, you've been given some diagrams and you have to describe what's going on. So it says, for each of the following, describe the motion of the object in words: constant velocity, accelerating, and indicate the direction of the net force. If there is more than one possible description, give both. Alright, so this is apparently some sort of object sitting on surface. It could be sitting on the ground, it could be sitting on a table, a chair, whatever. Okay? The force of gravity is always pulling it down. The normal force is holding it up, but it seems to be sitting there at rest. So the net force is 0. In this case, now we have an object has a weight, a normal force. It's on some sort of surface. It could be on the table again or across the ground. But now some sort of applied force is moving it, and there is friction force opposing it, but both of these arrows are in the same length, so this looks like it is moving, but everything is balanced, so it is going a constant velocity, and so your net force is still 0. 15, an object is initially moving to the right, so our gravity, our normal force, now our applied force, moving this object to the right, and this is our frictional force. Since they drew the arrow here, in this case longer than the frictional force, the net force is the applied force, and if the force of moving it is overcoming the friction and faster than the friction, then this is a case of accelerating. Object is initially moving to the left. Okay, so because it's moving to the left, that means that's the direction of our applied this time. Opposite of applied is friction, force of gravity, normal force. Okay, so now because it said it was moving to the left, our applied force this way, and then the line going this direction is the frictional force, so our net force is equal to the friction, and when frictional force is greater and there was a movement at causing the, or initially, so now the object is slowing down because friction is taking over the amount of the applied force. So here you have 4 scenarios: object at rest, object at constant velocity, object accelerating, object slowing down. This also might sound familiar when we were doing graphing kinematics, position time graphs at rest, constant velocity, acceleration curve, slowing down curves. Okay, so we're going to be putting all of those things that we've learned so far together. Last 2, skydiver just after opening a parachute, force of gravity is pulling him down, the force of the air resistance or drag, and in this case they drew the line larger here, so our net force is drag. Okay, because I'm going to write this here, the parachute is slowing down, the force of gravity. Okay, because when he was falling through the air, he was going at a pretty fast speed, and so in order to slow himself down so he doesn't hit the ground at terminal velocity, the parachute is supposed to slow him down. Okay, now the skydiver, a long time after opening the parachute, now force of gravity has balanced out with the drag, and so the net force is 0, and he's coming towards the ground at a constant velocity. under a control velocity. Okay? Alright, so if there's anything you didn't catch that I went too fast on, you can always go back, rewind, pause, stop, whatever you need to do to get all this in on your paper.